Benford's law. First of all, has anybody heard of Benford's law before? Out of curiosity, kind of. I figured everyone, but figured it would be you. But no, I just started reading about it. It's a topic that interests me. I figured there would be something I could relate to the stuff we've been learning in finance statistics and things like this. So first off, I should probably give credit where credit's due. This is Simon Newcomb. He was the first person to come across this, phenomenon. It was while he was shuffling through logarithmic books doing, he's a physicist back in the 1800s, and he noticed that at the beginning of the books, those pages were worn, the pages that represent the logarithms of 1, 2, 3, and as he got farther down, the 8, 9, and the 7, 8, 9s were hardly touched, and he knew this was less than a coincidence, so published a paper on it, but it wasn't really recognized at its time until the 1930s when Frank Benford, working for GE, also noticed the same thing. So he wrote his paper, but it was much lengthier, and he was able to put an algebraic formula to what he had noticed, and instead of just sort of, explaining it for what he saw, he could explain how it worked. Also, just a little thing, it's a good example of Stiegler's law. It's like a sociology type thing where the law is not ever actually named after the person who discovered it. They just sort of get lucky. It's sort of the second guy around. But so what the law actually states is that when you count through data sets of naturally occurring random numbers, the first digit or the first couple of digits will always be towards the lower end of the spectrum, and as you get higher up towards 8 and 9, the percentages go way down to almost nothing. Think of it as, I use this sort of helped me when I was trying to imagine how this all works, because the Indianapolis street system, starts at the 0 right at the circle, and then as you go out further, the numbers go up in each direction. So we figure like within the first block, you have evens between, it's evenly distributed between 1 and 9, and then once you get out to 10th Street, you have a whole mile between 10th and 20th, where it's all the digits start with 1 of the addresses. And then as you approach 100th Street, it all evens out again because you have a mile starting with 1, 2, 3, 4. And once you get to 100, you have 10 miles that all start with 1. So by the time you get through the ones again, you're back to where 1 is dominating the leading digit frequencies at about 55%. So I just sort of made this up because it would always help me when I sort of got bogged down with the math, just sort of visual aid. So this is the algebraic way to describe how to calculate the frequencies, ideally through Benford. You can see that for the number 1, it's basically the log of 1 plus 1 over 1. So it would be the log of 2, and it comes out to about 30%. And then a dramatic drop off as you go to 2, it's 17, and by the time you get to 9, it's only about 4%. This is what it looks like graphically. The same if you're trying to calculate just the second digit. You sort of sum the probabilities of all, sum the probabilities like the first digit's 1, 2, 3, 4, keeping the second one constant at 1. So the probability that the second digit of any given number is 1 is 11.4. And you can see that it gets a little bit closer to more uniformly distributed. And this is all three of them together. The blue is first, the red is the second digit, and the green is the third. You can see that the green sort of hovers right around 10% as it should, 0 through 9. And you can also use it for the first two digits in tandem with 10 through 99 inclusive. This is what they would all look like. So some sets of data that there's certain requirements that you have to use. They have to be naturally random. They can't be tampered with by a human, and they can't have discrete endpoints. Like, say you were to measure the heights of, U.S. males, you're not going to get any, 1,000-footers. So that would have a limited range. They tend to follow a geometric series. like you can see in this difference equation, just exponentially going up by a common ratio. And using larger data sets obviously helps anything when you're running statistical tests. And the more amount of figures you have, the higher you're going to run through a log table, so you'll be able to see a greater, a more consistent distribution of what you're trying to look at. So this is, the red is how Benford should look, and this is just 5,000 randomly drawn numbers between 1 and a million. So as you can see, what you would expect, they're fairly uniform across the board. And so here's the data that Benford used when he was first trying to pattern his results to things he found in nature, like the area of the surface area of rivers, different constants found in science and nature, molar mass. He used baseball statistics, anything that he thought could be naturally occurring and could fit what he had seen. And down here when you see the averages, you can see the percentages do align with his results. So here's just some of the data I pulled. I went through government websites. These are teacher salaries for Hamilton County, Hamilton Southeastern School District. And as you can see, there are a few outliers, and I've come to realize that the teacher salary cap is around $75,000. That's why there's a lot of the older teachers make the peaks out there, and the increase in population, I think, explains for a lot of the 50,000 area. And up here, you can see the first digit, how it matches up, and the purple and the green lines are for the upper bounds and lower bounds for a 95% confidence interval, which most of the bars fit in there. See, there's the outlier at 7 and at 5. So when you use Indiana University employees, which is 10,000 employees, the distribution gets a lot closer to the way it should be. By increasing your number, obviously, things tend to even out. This is county populations for Indiana and U.S. county populations. So up here, I think there was 3,800 counties in the United States, and Indiana obviously just 92. So it shows again more data to pull from the closer you get. And this one is the best because it's the most natural and it has the highest amount of data points. These are the distances of 48,000 of the stars in the Milky Way galaxy. And these seem to fit everything quite nicely. And so in the 70s and 80s, people had begun to use Benford's research to apply it to other fields such as forensics and data analysis. And Mark DeBraney is down here. He's still a professor at West Virginia, but he has written by far the most comprehensive book there is out there now. Costs $69.99 on Amazon.com if anyone needs it. And yeah, his evidence for inconsistencies have been admitted into state, local, federal trials. They've been used as a red flag, but not as any sort of means for prosecution. It's just a way to explain why a company got investigated in the first place. These are some of the reasons to trust Benford's law and how it works, but not to hold it as a hard and fast reason for investigation. Because if you have to say you have a car lot, and there's plenty of reasons why there could be a spike in the digits 4, 9, and you have a sale, or there's a tax lien if you go under 5,000, things like this. And it could be used in statistical polling. It's sort of a way of tricking the general population into thinking that their questionnaire is more random than it should be. If you tell them to use their address as sort of a randomizer, they will think that it's even as it should be, but you can get almost 78% of your data to be factual instead of, it makes the holster more honest. And here's just some things I messed around with, but I artificially made a Benford out of a uniform distribution, so, but you have to uniform it several times on over itself, which shows that naturals or numbers should be natural and not computer generated. And here's a die, the 6 die, or 4 dice thrown. This graph shows the product of the 4, and you can see how inconsistent it is because there's between the 6 you can only get multiples of those so many ways. The prime numbers are left out, and a lot of these have spikes at 12 because 1, 2, 3, 4, and 6 all multiply to 12. That's a way that that's definitely a graph that does not fit the mold, and that's it. Any questions?
You said that Stigler's law is that laws in mathematics and science tend to be made not after the person who discovers them, but after the person who makes them popular. Do we know who discovered Stigler's law?
Yes, and it was Stigler. He made sure not to make that mistake. He named it and easily thought of it.